Hello everyone, this is Elaheh from the University of Virginia, and today I'm presenting our work FlexAmata, an algorithm solution which enables a universal mapping of any pattern matching application to the existing and future memory-centric pattern processing hardware accelerators. So the first thing that comes to mind when talking about pattern matching is probably regular expressions, where it's commonly used in things like Linux grep command or to check the syntax of an email address. However, it's truly more than that. So pattern processing is an important operation used in many big data applications, where the patterns from these applications sometimes are represented directly as regular expressions, such as in network security, and sometimes they are not obviously mapped to regex processing, such as calculating string similarities in genome sequencing. And the problem is that patterns from these applications are often very complex, and they need to support a variety of inexact matches. And also for the real-time requirements, many of these patterns need to be processed at the same time, and therefore scalable and high-performance techniques for pattern processing are needed to keep up with industrial demand. So an example of that is in network security, when the incoming network packet is checked against thousands of signature rules to detect possible network attacks, such as intrusion, viruses, and spam. And this is a very simple example of such rules, where it says that if incoming network packet is coming from any IP address and any port address to this specific IP address with this messaging and argument, then an alert in a system will be generated. And the problem is that the number and complexity of such rules are increasing, and also the network line rate is increasing to eventually hundreds of gigabits per second, and the network intrusion detection system should be able to keep up with that rate. Finite automata are an efficient computational model for widely used pattern recognition languages such as regular expressions. So a regular expression can be represented either with deterministic finite automata or non-deterministic finite automata, or NFA, which in short, NFA allows for many concurrent active states and transitions, which results in a more compact representation in comparison with DFA. And here is an example of an NFA with several states and transition rules, and with a start state S0 and a reporting state S4, and assume that the current active state is a state 0, and if the next incoming symbol is A, then both S0 and S1 will be activated, and if the next symbol is B, then all these three states will be activated, and once you see a C, then a report in a system will be generated, and you see that how several states and transitions can be activated at the same time. Several CPU and GPU solutions are proposed to speed up the task, but the problem with von Neumann's solution is that the behavior of NFA processing is unpredictable, and it depends on the current active state and incoming input symbol. And also, the number of patterns is very large, and they usually do not fit into the on-chip caches, and this is combined with unpredictable behavior and causes a lot of cache misses. And also, there are many parallel transitions and also many parallel patterns that are processing at the same time, which means that there are a lot of parallel accesses to the memories, which saturates the memory bandwidth. To address these challenges, memory-centric solutions are proposed, and what they mainly do is that they implement NFA directly in hardware, and this allows a large number of patterns to be executed in parallel up to the hardware capacity. And now let's see why memory-centric architectures are ideal candidates for pattern processing tasks. So first of all, there are many applications that can benefit from accelerated pattern processing, and as we just observed, the nature of this problem is memory-bound in von Neumann architectures. And also the nature of this problem exposes a lot of parallelism, which can leverage bit-level parallelism in memory. And more importantly, the nature of this computation is very simple. So for NFA, we need simple comparisons and providing a network interconnect. Now I'm going to give you a brief overview on how an NFA can be processed in an in-memory architecture. Here is the classical representation of an NFA which detects this language, and we then convert it to homogeneous representation, which is functionally equivalent to the classical NFA, but in homogeneous representation, all transitions entering a state must happen on the same input symbol, and this provides a nice property that aligns well with a hardware implementation that finds matching a state in one clock cycle and allows a label-independent interconnect. On the right side, we see a simplified structure of a memory subarray with memory columns, memory rows, the memory decoder, and also the row buffer. And what we do is that we repurpose this memory subarray to encode the alphabets in each state of an NFA in one memory column with one hot encoding. And for simplicity, assume that we have 4 unique symbols A, T, C, G here. And therefore, 4 memory rows are enough to encode these 4 symbols. And instead of having a row address as the input of the decoder, we decode the current input symbol and activate the corresponding row with that symbol. For example, the symbol S0, the symbols in the state S0s are A and C, so we write 1 in the corresponding locations. Now let's assume that the current active state is S0. So when the next incoming input symbol is C, then S0 and S1 are going to be the next active states. And now let's see how it's calculated. So first of all, we look at the states that are connected to S0, which are S0, S1, and S2, and we call it potential next states. And then we look at the states that will be activated with symbol C, which are S0 and S1, which are the state match vector. And then what we do at the end is that doing the bitwise AND operation between these two vectors in order to find the next active state. And now let's see how it's done actually in the hardware. In the memory subarray, symbol C is read and then decoded, and the third row is selected, and the value is read into the row buffer, which are actually the state match vector value. And then to find the potential next state, we use a memory mapped full crossbar interconnect. So this is actually a memory subarray, and the intersections are the memory cells. And we write 1 in the locations that there is a transition between any two states. For example, S0 is connected to S0, S1, and S2. And then these corresponding locations, we write 1 in those intersections. And then, in order to do the AND operation, we add the logical AND gates in order to perform AND operation between the potential next states and the state match vector in order to find the active state vector. The main issue for all the existing in-memory accelerators for pattern processing is that they are based on a fixed 8-bit processing, which mostly comes from the byte-oriented text and packet processing. However, applications are diverse and they can have from a few up to billions unique symbols. And this incompatibility causes resource underutilization, mapping infeasibility, and future design incompatibility. Now let's look at each issue in more detail. So the first problem is the resource underutilization. So there are some applications where the number of unique symbols or unique alphabets is very small. For example, in genome sequencing, the number of alphabets is only A, T, C, and G, and with one hot encoding, only 4 memory rows are enough to encode these 4 symbols, and the rest of the rows are going to be underutilized. So for some application, the fixed 8-bit processing causes resource underutilization. So the second problem is that the existing 8-bit processing architecture cannot provide a support for the application with more than 256 symbols. So if you are mining a dataset from Amazon, the number of unique alphabets or items can be up to the 2 to the power of 20. And the underlying architecture should be able to provide a support for that, but with 8-bit architecture, you can only support 2 to the 8 number of symbols. And one obvious way is to increase the number of rows in a memory column, and with each bit that you are increasing, you are exponentially increasing the number of rows. And it's actually impractical due to the delay, power issue, and also signal integrity. And another solution is daisy chaining the states in order to be able to provide a support for a larger alphabet. But the problem is that simply daisy chaining a state results in a false report generation. For example, here, the left state, which has 16-bit symbols, if you daisy chain it in order to be able to use the existing 8-bit accelerators, the AD will be a false report generation in your automaton. And therefore, the existing 8-bit processing architectures are not general in order to be able to support these kind of applications. And the third problem is the future design incompatibility. So for example, Cache Automaton from the University of Michigan repurposes the L3 caches in order to implement the automata processing by repurposing the on-chip caches. And if the subarray sizes of the future technology changes, then you cannot map your application to this architecture. And therefore, the application may not be compatible with the future memory technologies. There are several research questions that we need to answer here. For example, how to efficiently support application with very large or very small number of unique symbols on the existing 8-bit processing accelerators. So how we can increase the resource utilization by having an application to make better use of the existing spatial hardware resources. And what is the best bit width size for automata processing on spatial platforms, and how actually design the next generation automata accelerators which have higher throughput and better efficiency. To address these questions, we present FlexAmata, which is a compiler solution that decouples the application with any alphabet size from the detail of the memory architecture. And at its core, FlexAmata acts as an adjustable range, and it takes an automaton which is designed to process n-bit symbols to another automaton which can process m-bit symbols where m can be smaller and larger than n. And of course, the m-bit design and n-bit design are functionally equivalent. And then you can change the size of m in order to trade off throughput versus area. And FlexAmata enables the universal adoption of any application with any symbol set size to architectures that can either be fixed 8-bit processing rate or the future architectures that can have different memory subarray sizes. And also, it also provides a resource utilization and efficiency. For example, if you're having an application with only 4 alphabets like ATCG, what you can do is that the existing automata is 2-bit design because you have only 4 alphabets, and then you can transform it to another automaton which can process 8-bit symbols. And what you've done here is that instead of processing 1 2-bit symbol per cycle, now you can process 4 2-bit symbols per cycle. And in this way, you are utilizing all your hardware resources, and at the same time, you're increasing the throughput. And it provides feasibility. So if you're having an application with a large number of symbol set, what you can do is that you can convert like 100-bit automata to an 8-bit automata using the FlexAmata engine and be able to utilize the existing accelerators for that. So there are interesting applications. For example, in verification, there are complex reactive systems such as aerospace and autonomous vehicles, and their main goal is that to convert the system traces to finite automata. And the main problem here is that the number of unique variables is in the order of 2 to the power of 100, and you can have this application converted to the 8-bit processing and use the existing architectures. And it also provides a compatibility. So if the subarray sizes of the future memory technologies changes, then you can use this engine in order to provide a compatible solution for your applications. And in addition, this tool provides design space exploration for other researchers to design the future memory-centric accelerators. So we use the temporal transformation to convert an 8-bit automaton to a 1-bit automaton, and then performing some bit level optimizations, and then convert a 1-bit automaton to any target bit width that we are looking for example, to a 3-bit automaton or to a 4-bit automaton. And I'm not going to go into the detail of these transformations, and the algorithm and the details can be found here. So what is the transformation overhead when you are converting from an n-bit automaton to an m-bit automaton? Now let's quickly see an example of converting an 8-bit design to a 1-bit, 2-bit, 3-bit, 4-bit, 7-bit, 8-bit, and 16-bit design. And our main observation is that even-sized transformations such as 2-bit, 4-bit, and 16-bit have lower state and transitions overhead. And you can see that how FlexAmata can minimize the original 8-bit design here. This slide summarizes the state and transition overhead on 20 applications. So the green bar shows the state overhead normalized to the original 8-bit design, and the blue bar shows the transition overhead normalized to the original 8-bit design in different bit width sizes. So the hardware implication for smaller bit width sizes is that the processing rate decreases, but on the positive side, the memory subarray size will be much smaller, which result in power and performance efficiencies. For example, in 4-bit design, the memory subarray size will be 16 times smaller than the one in 8-bit design. However, the throughput will be halved in 4-bit design because instead of processing 8-bit symbols, now you are processing 4-bit symbols. And the hardware implications for the larger bit width design is that the processing rate will increases, but on the other hand, the memory subarray size would be much larger in terms of the number of rows in order to be able to support larger alphabets. For example, in 16-bit design, the throughput will be doubled, and this is because instead of processing 8-bit symbols, now you are processing 16-bit symbols. Now I'm going to show you two case studies, one for an application with a small alphabet size to show how FlexAmata can enable higher utilization, which results in higher efficiency, and another one for an application with a very large alphabet size and show how FlexAmata can provide feasibility support. So for the first one, we use the string matching kernel in genome sequencing and with only 4 alphabets. So the automata design is 2-bit design, and we transform it to an 8-bit automata using the FlexAmata engine. And then we calculated the throughput per unit area for both the original design and the FlexAmata design. So the x-axis here shows the different read sizes in genome sequencing, and we found that FlexAmata can enable about 2 times higher throughput per unit area compared to the original design. And then we looked at another application in data mining with pattern matching kernel, where the number of unique alphabets in that specific application is 2 to the power of 14, which means that the original automata design will have 14-bit symbols. And then we use the FlexAmata engine to convert it to 8-bit automata and be able to utilize the existing 8-bit automata accelerators. So these graphs show the state and transition overhead when converting a 14-bit design to an 8-bit design in different sequence sizes. And we see that this overhead is less than 2 times for both states and transitions, which is a very small price to pay for the feasibility. Now let's briefly look at the framework that enables all these optimizations for us. So we developed APSim, which is an automata processing framework, and as its input, it accepts either regular expressions or an XML-based language, which you can describe an automaton with that. And then in the compiler side, it does all those bit level and byte level or symbol level transformations and minimization and compression techniques, and also the automata simulations to get the reporting data. And then the validation stage, making sure that all this transformation doesn't change the functionality, original functionality. And then for the backend, we are having FPGA backend for prototyping and doing some design space exploration, which that work was recently accepted in FCCM. And then the emulation for the in-memory architectures with design space exploration and different interconnect design, and also reporting architectures. And other researchers can use this tool in order to do a lot of design space exploration and design the next generation processing in-memory architectures. There are many evaluations on different in-memory architectures and FPGA designs for different bit width sizes in our paper for the interested readers, but the main takeaway from our FlexAmata work is that it enables a universal mapping of applications with any alphabet size to the existing and future memory-centric architectures, And it provides a design space exploration framework to explore different bit width sizes, which results in throughput, area, and energy efficiency. And it shows that how co-designing across the hierarchy can result in a better processing in memory solutions. Our framework includes the FlexAmata engine and can be found here in our GitHub. Thank you for listening, and please contact the authors if you have any question or if you are interested in using our framework for your own research.